All right, so hi everybody, welcome to this week's AFMS seminar. It's my pleasure to introduce our speaker for today, Professor Andrea Beck from the Otto-von-Guericke University in Germany. Professor Beck received her doctoral degree from the University of Stuttgart in computational fluid dynamics, and her interests include numerical discretization schemes for multi-scale multi-physics problems, and she's going to be talking about some of her research today. So please take it away, Andrea.
Thank you very much. Thank you, everybody, for coming to my talk. Thanks to Vishal and Kat for inviting me. I've never been to Australia, so this is a first good start to get to know you folks and then present some of my work. So I'm very honored to be here. I'd like today to give my perspective on data-driven computational fluid dynamics, what that means and how we can combine machine learning methods and classical computational fluid dynamics. And let me check. And my background is in those classical computational fluid dynamics methods, in particular in high order schemes. I'm not sure. One second, I have some issue here. Let me first move that out of the way. Okay. So my background is in high order schemes, and I'm not sure if you guys are familiar with what high order schemes are, but I'll not talk about them today. We'll move that out of the way and I'll introduce it where it's needed. Just to kind of show you what I usually do, my day job when I don't do machine learning, is I work on those schemes which are called discontinuous Galerkin schemes. And they are a method of discretizing the Navier-Stokes equations that has some nice properties in that it combines some of the advantages of finite volume schemes and finite element schemes. And in particular, these schemes can be made to high order schemes, which means very accurate and very efficient schemes for a certain number of degrees of freedom very easily. And my group and the group of also Professor Munz in Stuttgart spent about 10 years or so, spent the last 10 years or so developing a code framework that's open source, has all the pre-processing and post-processing tools in place called Flexi, and that is essentially the main workhorse that we use for solving the compressible Navier-Stokes equations and looking at detailed simulations of turbulence. So if you're interested in that code development, the method, we can maybe talk about that later. So here's just in a nutshell what this method looks like. So it's essentially, as I said, a hybrid of a finite volume and a finite element method based on a weak formulation of the governing equations or projecting the equations onto some test space and then solving that in a very efficient manner for us, it's tensor product elements. But as I said, I don't want to go into too many details on the scheme itself. So as I said, Flexi came out of this. And just to show you what we can do with Flexi, or what a typical size of Flexi run would be, I've shown here some numbers in terms of grid cells and degrees of freedom. So we run it up to 10 to the power of 9, or even maybe a little bit higher than that, degrees of freedom regularly. It usually runs on 60,000 to 500,000 cores on the local machine. So we use it for really, at least for us, really big problems, DNS and LES. And just some nice pictures to kind of close off this brief intro session. Here is what the types of problems we're interested in, some nice simulations, some nice visualizations of simulations that we do. So it's most of the time it's single phase DNS and LES, but we also dabbling a little bit into multi-phase, particle lane flows in turbo machines, aeroacoustics, uncertainty quantification. So everything that's kind of can be related to this core application of turbulent flows. One last slide, because it's very recent work of two of my students that we are pretty proud of. I want to show is the first one here is what you see up here is a water droplet that's hit by a shock wave. So the shock wave smashes into it and it deforms this droplet and leaves this sad little shape here. But what I wanted to show here is that our scheme, our code framework is highly adaptive to the local flow features. So what you see here on the left is the density, and what you see here on the right is different discretization operators that we choose according to the flow physics. So for example, Here we have a strong gradient here where we have the phase interface. Then we would do something akin to a shock capturing approach. And where we have those vertical structures here, we will essentially increase the local resolution, increase the local polynomial degree to capture them as accurately as possible. So that's something that a student of mine did and that I like a lot. And the second one, where we're doing icing on wind turbine airfoils. We're interested in finding out under what conditions does icing occur and how dangerous is it. Well, for wind turbines, it just reduces efficiency, but for aircraft, it could, of course, lead to stall and crashes. And he was able to do some uncertainty quantification, Monte Carlo simulations for different ice shapes. You can see those black horns here protruding from the leading edge, and then we analyzed how the flow field looks like also with Elias. Okay, so that was just a little bit advertisement for my group. And now let's come to the main part of today's talk. So I want to give some examples of how we can fuse machine learning and computational fluid dynamics. And the first example I brought will be from shock capturing for these types of methods I just talked about. Before I jump into the shock capturing, let me just introduce supervised learning, which we will use in the shock capturing on a single slide, because we will use that through, well, the next half of my talk. I assume that many of you have by now come across neural networks and supervised learning. And just to maybe remind you is supervised learning is a method of learning to extract a relationship between an input vector and an output vector based on data. We make an assumption about this mapping between those two, and we cast this assumption into a neural network. So the neural network is essentially gives us the structure of the mapping. You can do that with other approximations as well, but neural networks are just the Swiss Army knife of machine learning methods. So we stick a neural network in there. And this neural network is usually drawn as this nice graph here, which is just a fancy way of well, essentially showing matrices and activation functions in there. And optimizing the weights or the entries of the matrices in here is what's done through typical computing an error term and then computing a gradient and updating that through gradient descent. So this is by no means a complete introduction, but just to remind you, supervised learning, I have a bunch of data. I assume a relationship between them. The relationship has some parameters, and I update these parameters through an iterative process. Okay, so just let's keep this in the back of our minds. And now let's see how we can use this and combine it with classical CFD for, in this case, shock capturing. I've talked to Vishal before, so I know that you all are from the fluids or applied math communities, so you know that compressible flows are very interesting because then they can exhibit something like shocks. So shock is essentially a discontinuity or a very, very steep gradient in the flow field. So when you want to treat them numerically, that means if you want to simulate them in your code, you have to do something specifically. You have to tweak your numerics to make sure that you capture this shock, that you can represent this shock faithfully, accurately, and stably. This is called shock capturing, at least in my community. Different communities might use different words for that. But this shock capturing is something that you need to do to your numerical scheme to get the shock good and right. However, before you can do that, you first need to detect where the shock is going to be, because you only want to apply this special numerics, this band-aid, so to speak, right where you need it. So you need to detect where the shock is going to occur. So first thing is to do that through what's called shock detectors or shock indicators. And they are essentially, well, indicators that have some empiricism in them, some fudge factors that you tune out of your experience and say, okay, if my indicator gives me this value, then this is likely going to be a shock, and if not, then not. So this is where a lot of empiricism comes in, and this is kind of akin to turbulence modeling. There are many of those indicators out there, and people always use their favorite one and try to run a stable simulation. The way this usually works out of practice, if you have if you have a student or if you try it yourself, you set this indicator to a certain value, you try to run the case, and if it crashes, you just make the indicator a little bit sharper, you rerun and you rerun. So it can be quite laborsome. So detecting the shock is a challenge, and detecting shocks for the methods I'm interested in, those high order methods, is particularly challenging because the high order methods, they have grid cells that are much larger than what you might be used to if you're running a finite volume scheme, for example. Think about high order finite element grids if you're familiar with that. Or, as I said, if you're familiar with finite volume schemes, then a finite volume cell for such an airfoil here would be this light gray guy here. And the cells I'm using, they are the big black ones. So we have large cells and we have an inner cell resolution. That is just to say that just detecting which element, which grid cell might contain a shock is not sufficient for these types of methods. But instead, what we need is to have a localization of the shock on the element subscale. So I want to know not just the element the shock is in, but where precisely in my element the shock is going to be. So this is an additional challenge for those high order methods, a shock capturing for high order methods. Just to set the scene a bit, there are essentially two types of shock capturing people can use. The first one is discretization-based shock capturing. So when shock occurs, you just switch your discretization to one that's guaranteed stable at shocks. So there are specific schemes that can be shown to be provably stable in such conditions. It's essentially always the idea of using less accurate, more dissipative schemes at shocks, and then moving to more accurate and, sorry, did I say less dissipative, more dissipative schemes. So less accurate, more dissipative schemes at shocks that kind of smear out the gradient and then capture that. And the second method is the artificial viscosity-based approach that leaves the discretization operator as is, but adds a local viscosity that does what I just described. It smears out the gradient and makes it capturable on the current grid. Okay, just to inform yourself. So the idea that we now had was we had these empirical shock indicators that people have been using. We played around with the parameters and we were dissatisfied with having to come up with fiddling with the parameters or having to fiddle with the parameters for each and every simulation. So our idea was to use a supervised learn a classifier that tells us, does an element contain a shock or not? And do that based on artificial training data. So here is a sample of what this artificial training data looks like. So we've just shown the 2D cases here. So we have set up a number of 2D elements. We have used analytical solutions that are smooth or non-smooth, so that are shocks or non-shocks, have combined them in some random manner and generated tens of thousands of training samples for us, where for each training sample, we know a priori, well, it contains a shock because we chose it. We chose that it should contain a shock, or it's just a smooth solution. So we can generate as many smooth, non-smooth samples as we want. We know their labels, and now we can train them with supervised learning. It's pretty old work, so TensorFlow was really 1.6 back then, but in any case, we did it back then, and it worked with those technical details given here. I'm showing you some of the results here, where we use this just to flag the element in our grid that contains a shock. Here are some classical test cases from compressible aerodynamics, 2D and 1D Riemann problems they're called. They're essentially just forcing some shocks and associated waves to occur in very simple geometries, just by setting the initial and boundary conditions. And you can just see by visual inspection, you can see here from the density where you would expect a shock to occur. And you can see down here that our shock detector, trained in the supervised manner, is very capable of detecting and showing us nicely where the shocks will be located. Not just that, it's also stable, right? So we start all these simulations essentially from a free stream. And then once you let it run, those shocks instantaneously move in and appear. This is usually the tricky part in getting these problems right. And this also worked with the shock indicators that we trained. So that's the good news, right? We have a machine learning indicator that tells us where we can expect those shocks. Comparing our approach, which is the first column, to the more established approaches where we hand-tuned empirical indicators, we see a very nice result. First of all, the ones we trained, or the one we trained, is in terms of accuracy, in terms of what you would like it to predict, completely comparable to a well hand-tuned indicator that we had used before. And that's what I want to show on the next slide, is we don't have any fudge factors anymore. So we just take this indicator, we plug it into our code, we use it, and we can also use it on different grid resolutions. So if you change your grid resolution, in the old case, you would likely have to retune your parameter, but here we just take this parameter, take this indicator, plug it in, and it works on different grids. This was a nice success at first, but we weren't quite satisfied with that. We thought, can we go on and do something more? And the answer was, we don't just need a shock detector, but we need a shock locator. And by locator, I mean what I showed you on this previous slide here. I not just want to know which of these large elements has a shock, but I want to know where in the element, essentially this yellow curve here, where in the element the shock is going to be. So how do we do that? Well, we borrow ideas from edge detection. There are many machine learning applications that deal with how to detect edges in images. And we borrowed one of their ideas and adapted it to our scheme. So the basic idea is we have a single of our grid elements. Within each element, we have this sub-element resolution. So we have some degrees of freedom within each element. We treat that as an image that we put into a whatever type of neural network we choose, and then we apply methods from from edge detection to tell us where in this image does an edge occur, right? And for us, an edge is a shock. So if we feed it a pressure distribution, for example, right? Then if this is a pressure distribution, then the image detection algorithm will tell, oh, there is a gradient here, there is a jump here, there is an edge here. But for us, we'll realize, okay, this is actually a shock that we are seeing here. So maybe I explained that in a complicated way. So the idea is to recognize that shocks are essentially sharp gradients, are essentially edges if you look at them, and then use methods for machine learning that are made for detecting such edges. The method that we use, and we tweaked it a little bit, is from multi-scale convolutional neural networks. So convolutional neural networks are great because they allow you to operate on volume or tensor data, essentially. They are shift invariant, so it doesn't matter if your shock appears in the lower left corner or the upper right. And you can do something that's called multi-scale CNNs with them, which is essentially a clever combination of ideas from linear algebra and machine learning. And what it does is it makes use of the fact that edges are scale invariant. So that is to say, if you have an image and you zoom in very closely, an edge will always stand out as an edge. When if you zoom away, it will be at the same position and it will always be there. So no matter how much you zoom in or you zoom out, no matter what scale you look at this edge, it will always be there. So this is the idea of a multi-scale CNN, combining essentially different fields of view on the same property, and then identifying a feature that stands out. And this is where the shock detection comes in. Okay, so I guess I have to speed up a bit. So we have time for the turbulence part later on. So this is where we came up with a shock locator. So extended this idea. Again, I'll do it in supervised learning because we can, in the training data, say, okay, I'm training on analytical solutions and analytical shocks. So, excuse me. So of course, I know where my shock will be. And here are some of the results that we came up with. First of all, training works well, surprisingly well, actually. And we can essentially have for the shock locator the same properties as we had for the shock detector. We don't need to retrain it. We don't need to put in any parameters. Just take this trained neural network and use it as a shock locator. And the results are quite nice. So on the left-hand side, again, we have our standard test case called a double Mach reflection. And everywhere where you see a sharp color gradient here in the density, that's where you would like to have a shock over here. And what you can see is that, first of all, the shock locator nicely tells us where the shocks will be. It does that in a continuous manner. So the shock fronts are indeed continuous. There are no holes or other fancy things going on there. It is consistent for varying resolutions. So if I increase the resolution but change nothing else, my detection of where my shock fronts will be also converges. And it also works nicely on unstructured, rather bad grids. I intentionally made a pretty bad grid here for this airfoil case. Normally, I would, of course, make a more solution-adapted grid. So I made intentionally a very bad grid here. And you can see that it still gives me reasonable locations where the shock is going to be. And in particular, that's the point I want to stress. It does that. It tells me where within my element the shock is going to be. Look at this element over here, for example. I now know for this element precisely where my shock will be and precisely where I'll have to do something about it in terms of shock capturing. So out of this capability of telling not just the element, but where within the element we need to do something about it, came this idea of localized shock capturing. Let me say that this capability of not just flagging the element, but precisely locating the shock, at least in the high order community, is something new. So people before have only been able to tell, okay, the element contains a shock, but not within the element the shock will be. So with this machine learning approach, we now can do that. But we wanted to essentially close the loop and now use this information that we got from the numerics or got from the simulation to make our numerics better. And this is where we came up with the idea to use an improved version of artificial viscosity to improve our shock capturing. So improve our numerical method so it can be more accurate in dealing with these shocks. I mentioned before, the artificial viscosity approach is just we add some second order term to our equations. And all we have to, or what you have to do now, what you have to choose is where you actually add this viscosity term and how much viscosity you add locally. So you need to specify for an artificial viscosity shock capturing, how much viscosity and where will this viscosity be. And so far in those high order methods, people have always used an element-wise constant artificial viscosity. So just pick one value for each element and then maybe do a linear continuous reconstruction between elements. And we want to now take this a step further and say, hey, we know where within an element we actually need a high artificial viscosity, where the shock will be, and where we don't need an artificial viscosity. So let's see if we can come up with a more localized and smooth distribution of this artificial viscosity. So now we took this output that we got from our machine learning detector that tells us, okay, you have an element here, you have those nodal degrees of freedom, those circles, and just the black circles, they are the ones where we will have the shock. So now let's use this information and actually build an artificial viscosity field that is suited to this. So how did we do this? Well, we essentially used radial basis function interpolation, knowing that the artificial viscosity here should have a certain value and should be 0 at these other nodes. And then use different radial basis function interpolants to generate a smooth distribution of this artificial viscosity. Radial basis function interpolation leads to a globally coupled von der Monde matrix, but it's only weakly coupled, so we can reduce this without too much trouble to a local problem. We use different shapes and types of radial basis functions. Maybe that's not too important. The important message here is that you can essentially choose any radial basis function that you want, in particularly higher order, very localized ones. And this is what we'll see in the next slide, how local this can actually get. First of all, let's have a look at the results. So we have a standard shock tube test case here. So that's how people test their compressible codes and test their shock capturing schemes, which is called a shock tube problem. And I'm comparing my solutions with those adapted artificial viscosity in blue and in green, comparing them to the gray curve, which is the reference curve from a DNS essentially, and the red curve, which is the current state of the art in shock capturing with this constant artificial viscosity per element. And first of all, we see, well, our approach, if we apply it to this to this test case, works as expected. And now if we zoom in on the contact discontinuity here, we can already see that our blue and green curves are much closer, at least in my I-norm, are much closer to the actual reference solution than the current state of the art. Everything else being equal, same code, same everything, same grid. Only difference is how do we choose the artificial viscosity, and we choose it very locally by our indicator that is given through the machine learning. So this is quite nice, right? So the red state of the art doesn't contain any machine learning at all, just an indicator. You tweak it, you run it. This is the result you get. The green and the blue curves are the indicator. The shock indicator tells us, okay, this is where your shock is going to be, and this is how you should choose your artificial viscosity to make it very localized and stable as well. To make this a little bit clearer, here's another example, same colors. I'm zooming in on the actual artificial viscosity field. Okay, so I'm actually looking at what this artificial viscosity that the methods are giving us, what they look like. Again, same colors as before. So we have a shock located right here. And the old standard methods, the red and the orange one, they would give you what I described before, a constant artificial viscosity in each grid element, and then maybe a linear reconstruction. So what you're doing with this red method, you're applying a huge chunk of viscosity to this whole region here. And for our approach now, that tells us, hey, I know precisely where my shock will be, and I can use this RBF, this high order basis functions to target my viscosity. I can limit my viscosity to this blue or to this green region. And if you now look back over at the results, you can see that this results in a significant increase in accuracy. Again, everything else being equal, same grid. All we do is pick the artificial viscosity in a more intelligent, more localized manner. Okay, this also works for 2D problems, just to show you that it's not just limited to 1D, gives consistent results in 1D. And here I'm comparing our new method to other established shock capturing methods, which are from the discretization operator-based shock capturing. So what that means is I'm not using artificial viscosity to capture a shock, but I'm switching my discretization to a stable, highly dissipative discretization. This is what's shown here in this. You can see this inset grid here. So these white inset grid lines, that essentially means I'm switching essentially to an H refinement there, and then using a very fine grid with a finite volume scheme in here to capture the shocks. This is, if you look at the shock fronts, they are actually sharper than they are with my artificial viscosity based approach up here. However, all I have to do here in the upper part is to essentially implement an artificial viscosity method and then run it. Whereas down here, you have to implement an HP adaptive code scheme. So you have to have different discretization operators, interpolation and projection operators between the two transferring. So that's a lot more work. This is something that a student can essentially implement as a bachelor thesis. This is something that takes a full doctoral thesis to get to work. Okay, so this is just showing, well, it's not the sharpest shock you can get. Our method is sharper, or gives sharper shocks than the ones that we previously had. But it's a good alternative, a cheap alternative, and an accurate alternative to more elaborate shock capturing schemes. And this is just essentially repeating the same message, just on a way coarser grid. I like this image because it shows that, hey, with this method, we actually have grid cells this size here. And I can nicely, in this white region here, I can nicely capture my shock within a single element with this method. Okay. Can also, again, use this on very bad grids and maybe more interesting cases like an AKW12 case here. It's just repeating the message from the previous slide. So let me briefly summarize what we've seen here. So shock capturing is a problem for any numerical scheme. It's particularly tricky for high order methods where we need to have very localized shock prediction. We usually do that with empirical indicators. We went the supervised machine learning route and developed indicators that tell us precisely there the shock will be. We use that not just to run stable simulations, but also to improve the current shock capturing method, the current state of the art, to make it more targeted. And I've shown you that indeed this is an improvement over current existing methods. And it works nicely for us. So I think this is a nice example of how we can augment CFD with machine learning and kind of vice versa through a supervised learning manner and make actually, useful additions to CFD through machine learning. Maybe a personal comment, I've seen many people do a lot of interesting machine learning stuff, but when you combine it and try to make it actually useful, in engineering simulations, I think there is still a gap that we need to fill. All right, now let's come to the second part. And I realize I need to speed up a bit. Turbulence closures from data. So I asked Vishal before, you're all very knowledgeable about turbulence, so I'll essentially fly over this very quickly. So we all know that we cannot afford to solve DNS all the time. Instead, we need to do LES. We need to come up with a coarse-grained equation plus some closure term, Reynolds stresses or Reynolds forces, however you formulate that. And finding models for these closure terms is what RANS and LES people are after. The need to still find good LES models is, I always use this slide to show that. We have a very simple flow, standard canonical case, flow over a cylinder, Reynolds 3900. This is a DNS. I'd like to get a faithful LES representation of that. And then I need to, I want to compare the velocity here on the center line of this case here. So average velocity, very simple case, very simple setup. And I collected some data a while ago from literature where, to the best of my knowledge, everything else was the same equations, same domains. Most of them were also using the same LES model. But all the results completely different. It's very unfortunate, but this is the truth that comes if you compare different LES results for this case. And what's particularly depressing, two of these results are mine, the red and the blue one. They also differ, and none of the results come close to the experimental data. So there is a huge drive, at least from my perspective, or a huge need, I should say, for actually coming up with good LES models. And the trouble with LES does not just come from the models, and that's important. It comes from that we often are very imprecise in defining what we actually mean by we do an LES. And this starts with one important aspect, that the filter that we use, or each filter that we use, each type of filter leads to different Reynolds stresses, and thus would actually mean that we would need to adapt our closure models because we have different Reynolds stresses that we induce by the filters that we use. Here's to highlight this case. So I have a DNS, and this is essentially just a field of UU, and I'm applying different filters to this. This would be a local L2 projection filter akin to a DG discretization or a finite element discretization. This is the classical top hat and Fourier filter. And well, we all know that, of course, the solution fields, the filtered fields look different. But what took me a while to fully come to grips with is that Also, the induced Reynolds stresses look different. So there isn't the thing of the Reynolds stress, but it depends on the filter that you use. And it becomes more difficult or impossible even to define what this filter that you're using even is if you're doing what's called implicitly filtered LES, which is 99% of all the LES that people are actually using. Its mathematically nicer brother is the explicitly filtered LES, where we would actually use a well-defined filter with some filter with delta R that is separate from the discretization, which are characterized by H. That would mean in an explicit filtered scenario, I can converge under the filter, so I can keep my filter width and then converge my discretization. So my discretization scheme will not play any role. It doesn't matter in theory which discretization scheme I use to do that. It's just a function. What my Reynolds stresses would look like would just be a function of this filter kernel. There are some caveats with this. If you've worked with explicit LES, you know it's not so clear cut. But things get worse if we turn to what everybody else is using, which is implicitly filtered LES, meaning the discretization operator is the filter or acts as the filter. So what you can no longer do is actually converge your discretization, because that would mean you would converge to a DNS and not save any computational time. But it's important to keep in mind that the discretization scheme now defines the filter kernel. So I have all these troubles from over here that I need to take care of, all these commutation issues, plus I have my discretization parameters and my discretization errors in there. And this leads to what I like to call the LES dilemma, which is that if you look into a textbook, what the Reynolds stresses, the terms you should close are, this is what the textbook gives you. And this is nice because it's a priori computable. You know what your filter is. I can compute my term, so I know what my model should model, right? This term here, my best model should try to model this term. However, if you run a true simulation that is grid filtered, then my true closure term is not this guy up here, but it's actually this guy down here, where I don't know what my discretization operator does. So I don't know what my filter is. I have boundary conditions. I have stretched grids. I have, maybe switching my operator around. So that is to say that this guy here is what you actually get as a closure term during computation. It's not a priori computable. It actually appears during the discretization. Just maybe to drive this complexity home a little bit, let's return to one of the previous examples. And remember that now, if I want to compute an LES of this guy, of this case here, I have discretization operators that each element essentially has its own discretization operator. This region here is now a structured grid, but out here it becomes unstructured. So I have all these errors in there, all these commutation errors in there that make it impossible for me to a priori compute what my closure term actually is. So we have these two, let me go one back. We have these two cases here. If I can a priori compute what my closure term is, I have a chance of using that to inform supervised learning models. If I don't know what to aim for, then I'll have to come up with a different method for finding models for that. And I want to touch on both of them very briefly and seriously over time. So I'll probably skip through this first part here and then come to the second part in more detail. Let me summarize this first part where we focused on learning models for this term here. First of all, learning this term here, and then learning models for this term here through supervised learning. We have a bunch of papers on that. We did that with convolutional neural networks based on spatial data. We were pretty successful in doing that with temporal networks as well. And we got very, very accurate in predicting for very simple turbulence cases, homogeneous isotropic turbulence, in predicting actually this unknown term here just from data only. I'll show you an example and skip the rest of this section. The example would be this column here. So these are the exact Reynolds stresses on the test case, so on the unseen test data. And here in the middle column, you see what our best neural network prediction with a sequence network can actually do. And just in the I-norm, you can see we are about 99.9% accurate in predicting this, the actually unclosed term, the unknown term from coarse grid data only. So this was done in a supervised learning manner. We computed a bunch of DNSs of a homogeneous isotropic turbulence in a box, and then trained on that supervised learning manner, and then used that for the prediction. And as I said, there is a bunch of work on this. Maybe at a later date we can talk about this more. I want to skip on to. Let me show you this last slide maybe, so you get at least a feel for what these models that we came up with were able to do. So as I said, the homogeneous isotropic turbulence was our test case here. So we applied it to such. And what we came up with in the end, after some trials and errors, was a data-based eddy viscosity model, where we not just used the prediction for the Reynolds stresses directly, but instead projected the predicted Reynolds stresses onto an eddy viscosity model. And the results that we got are best visualized here in this kinetic energy graph here, where the black line is the filtered DNS kinetic energy for this case here. And all the other colors, they are different eddy viscosity or implicit LES models. The green one is a classical Smagorinsky model down here. And the one that we got, our eddy viscosity model, where the eddy viscosity again is computed by projecting the predicted Reynolds stresses, predicted through machine learning, onto an eddy viscosity basis, and where we ended up with the red curve here. So a clear improvement over the current existing method by picking an eddy viscosity from a supervised learning method. So to sum up this, because I really want to talk about the last part, a couple of minutes, is that from supervised learning, we learned that we can predict those closure terms here, these guys here, where we clearly have them a priori at hand if we have DNS data. We can predict them with previously unattainable accuracy, but we need to do something to actually use them in a computation. We need to, for example, project them onto an eddy viscosity basis or add some other form of stabilization, because just using this term turned out not to be very stable. So we did this both with convolutional neural networks and sequence neural networks, and the results were all comparable. But we always encountered this problem of, hey, I have very, very high a priori predictions. So they are great. They are 99.9% accurate a priori. But once I plug them into my LES and run them, they crash. And I need to come up with some fixes again. So we came up with a new idea, and that goes back to the second formulation here. This one here, realizing that, well, this is not the true closure term anyway, so let's work with this actual closure term during the computation. And that led to the new idea of using something completely different in terms of machine learning called reinforcement learning. I briefly introduced that, and most of you probably, I'm not sure if many of you have heard about that. So let's just give you an overview of what reinforcement learning actually is. Reinforcement learning is based on the idea of a Markov decision process. That's a fancy way or a mathematical term of saying I have a sequence of states and actions. So we think completely differently than from supervised learning. Now we're talking about a system being in a certain state and an action being taken that moves a system to another state. And if this happens, or once this happens, the system can emit a reward. I'll make an example that makes it clearer in a second what this actually means in real life. And such a process of having states and actions and then going on and on and on is Markovian if this whole thing is memoryless. So if all I need to know what's happening in the next stage is the current stage and I don't need any time history. The solution to such a Markov decision process, now it's a policy, and a policy is just a prescription for, okay, you are in a certain state, what action should you take now to achieve your final goal? Let's make a very simple example that I always think makes this rather complicated concept very clear, hopefully. So if you were to learn how to play chess, then this environment that we're talking about, the state that you were observing, would be a certain position of the pieces on the board. And the actions that you could take were, well, move one piece within the rules of chess to an allowable position. And then the cycle would repeat. You would observe a new state, new position on the board, and then your opponent would move, and so on and so on. So the state would be the state of the board. The actions would be make a move, and the reward could be, okay, I beat one of the opponent's pawns or whatever, or I end up winning the game. So this cycle keeps repeating. And now solving this problem, solving this Markov decision process would result in coming up with a so-called policy, pi, that is your strategy for playing chess. Okay, so this policy that we're after is the strategy of solving this problem, which, as you probably can tell, is an optimization problem, or it can be framed as a control problem for this policy pi here. Let's see how we can put this idea of playing chess towards finding closure models for LES. Well, here's a sketch where I try to show you how to do that. First of all, the environment that I'm dealing with now, my chessboard, so to speak, is now my forced LES over homogeneous isotropic turbulence with stationary statistics. So this is the state I'm observing. Or this is the test case I'm using, and the actual state I'm observing is now the numerical solution of this with an implicitly filtered LES with my favorite discretization scheme. So this is the Flexi framework I talked about with an implicitly filtered LES. Now my environment runs, that means my LES runs forward, and I have my actions that I'm taking are now picking for each element an eddy viscosity in space and time. So each of the grid elements here can now choose its own eddy viscosity in space and time. The guy that does that in reinforcement learning is called the agent. So the agent is the thing that has the policy inside. So this policy is just which eddy viscosity do you pick and choose. The agent in our case is encapsulated in a neural network again. And the reward that we are looking at is how well does now my LES computation, my implicit LES, how well does that now fit, for example, my DNS spectrum up to the cutoff frequency? Okay, so I give it this whole optimization loop. I ask it to optimize picking an eddy viscosity in space and time. And I judge it by how well it achieves this goal of, for example, matching a prescribed DNS spectrum. And once I have this set up as an MDP, I can now solve this through reinforcement learning. So reinforcement learning is a whole large field of methods. The ones we use is called, or is from the family of policy gradient methods. Details are not too important here. We can discuss them later if you're deep into reinforcement learning. Let me just state this for the general audience, because it's important to understand the basic idea behind reinforcement learning and not so much the specific details. Reinforcement learning is a different paradigm for machine learning in that what we are now doing is completely different from supervised learning. In supervised learning, we have an input and we have an output, and we know those two. And all we're asking the machine learning to do is to find this mapping, nonlinear, hierarchical, whatever, between the two. And now in reinforcement learning, well, we have an environment that is dynamically evolving. We can change this through the actions, and our optimization goal is achieving something, some end goal, so to speak, some winning the game of chess or getting a good turbulent spectrum out of this. So in this short sentence here, reinforcement learning is learning to take optimal actions in a dynamical system from experience to optimize an expected reward. And when people talk about the successes of reinforcement learning, they always talk about things like self-driving cars, autonomous robots, playing AlphaGo or StarCraft. And all of these real successes are actually driven by reinforcement learning, at least in parts. So I'll skip the mathematical details on how we do this optimization process. Let me just say it's not too, well, it's complicated in the details, but the basic idea is like with any optimization, you define an optimization problem to be some form of maximizer or minimizer. And what we maximize here is the expectation of, let me frame it in the term of chess, of winning the games of chess, or the expectation over how well can we perform our LES. We can compute the gradient of our cost function, again, through this rather complex formula. And all that we do in reinforcement learning now is essentially playing many of these games of chess and evaluating the current policy and coming up through this equation here with a gradient for our policy. Okay, so it helped me a lot to really think about this in terms of learning how to ride a bike or playing a game of chess. So what you do in reinforcement learning, you have a certain idea of how to play chess. And then what the reinforcement learning algorithm would do is use this idea, so your current knowledge encapsulated in your policy, and play as many games as it can, right, to find out how your policy is behaving, collect all this information, compute a gradient from that, and then do this all over again, or use the gradient to update your parameters and do this all over again. So it's always this idea of like you would learn how to play chess or ride a bike, right? Yeah, sample your current strategy, gather a lot of experience, and then improve upon that. Okay, so now let's come to what we can do with this, and I'll try to finish up quickly. So why did we go about this complicated way of learning, or coming up with a method of learning something as simply as an eddy viscosity? Well, because from my previous discussion, I said, well, the term that I'm trying to match here, my actual closure term that I'll have during the discretization or during the computation is unknown. So I cannot have success in trying to match that with supervised learning. Instead, I need to come up with an optimizer that is actually capable of dealing with this within the dynamical system. So finding within this dynamically evolving system, dynamics because of turbulence, dynamics because of nonlinear discretization, irregular grids, and so on. I need to come up with an optimization strategy that is capable of predicting this or giving me good estimates for this case here. So we can optimize our turbulence closure now, subject to the induced filter form of our discretization operator. So we can take this discretization operator into account because it's actually in the discretization or in the simulation, it's actually happening there. We need no DNS data to do this. All I need to do is run LES computations. I need to run many of them, but I don't need DNS data. Don't need to have this a priori available training data. I generate the training data on my own as I go. And essentially what this turns out to be is not just something I can use for LES, but what we've come up here is a trainable PDE solver. I'll show you in a second where we have stuck our CFD solver within or into such a reinforcement learning loop. Okay, now come a few slides on high performance computing and this framework. I'll again try to be brief. So like with any machine learning here, we need a lot of training data or training runs. So while we don't need to have DNS data for this case, we need to run quite a bunch of LES computations. So the overall efficiency of the full framework is important. Then we, of course, want to run our code on the CPU. It's a CPU code. We want to run the machine learning part on the GPU. So we need to come up with some form of framework that allows us to do that. And we're finally aiming for actually usable LES. So we want to have this framework also run on our supercomputer so we can actually use it in those large scale computations I showed you in the first part of my talk. So here's just what I mentioned in a nice sketch. This stuff here all runs in Fortran on the CPU. The current supercomputer that we have available is called Hawk. And we also have an AI extension to Hawk. And this network then and the training process all runs on the GPU. And we've come up with a nice framework that connects the two, allows us to do in-memory transfer. We have a paper on this, so I'll skip this part here, just to say that this is a nice joint work with Hewlett-Packard, who are the inventors of, well, first of all, are the vendors of the supercomputer that we work on. And then the SmartSim framework is also partly developed by them. And we kind of were the first ones to use this to actually have a full-fledged CPU code and use this in combination with machine learning on their system. Okay, I'll skip the scaling. Let me say it scales very well. And let's come to the actual results, showing you what we can do with this. I've now told a long story about reinforcement learning. Let me now show you some of the first results that we currently have that are very, very encouraging for a forced homogeneous isotropic turbulence. And then I'll close with that. So we use this as a test case. We have one DNS, that's the green spectrum, and we have an LES resolution that is up to here, to the red spectrum. As I said before, we train our reinforcement learning agent to give us a an eddy viscosity in space and time. We do this to this PPO algorithm. So the algorithm learns how to pick this mu at every element and at every point in time. We train this to, essentially follow all the technical standards that you do when you do machine learning training. Training on training data and evaluating it on the test data and all these good practices. And I want to show you I want to skip right to the results that we got with this. First of all, let me say that it's completely unclear a priori if this works or not. So the first good thing is we were very happy to see that it actually does work. And the second thing is we were surprised to see how well it works. So please don't expect any miracles from this. It's still an eddy viscosity model, but now with a cleverly picked eddy viscosity at each instance. I'm showing here the spectra for two cases. So let's focus on the left one first. The dark green curve in the background, that's the DNS, or the mean DNS spectrum. I'm showing here the cutoff frequency of my LES, so of my numerical scheme, meaning I would expect my numerical scheme to give me good, accurate spectral results up to there, but not beyond that. And the different colors now refer to different LES cases again. The interesting ones are the implicit LES, or implicitly modeled LES. In the high order community, that's currently considered somewhat the state of the art. So just use the discretization error itself as a closure model. That works sometimes well, sometimes not so well. In this case here, it works okay-ish, I would say, but not great. So that's the green curve we compare to. A classical Smagorinsky with a fixed constant, that is the pink curve here. And the trained reinforcement learning agent, that is the dark blue curve here, or this, well, not sure if that's dark blue, but the blue curve here that we see. So the great news is this works. The reinforcement learning agent actually picks a meaningful, stable, accurate eddy viscosity model. And we are even better than a classical Smagorinsky model. Let me say that for this case, stationary turbulence, with a classical Smagorinsky model, you can get near perfect accuracy, very, very good accuracy. So this is already a very, very nice result. And we get it up to the cutoff frequency of our scheme. And it also is transferable to a different numerical scheme, slightly different grid, different polynomial degree, different formulation, meaning what I'm doing here is I'm changing the filter form. Implicitly filtered LES. My discretization defines my filter kernel. So different discretization means a different filter form. So what I'm showing you here is that this approach also works if I now have a changing discretization scheme, if I have another filter kernel, this is what I set out to, what gave me the trouble in the beginning. Same colors again. And now we can see that for this case here, our blue curve, our trained reinforcement learning agent, actually works near perfect, right? So it's near on top of the DNS spectra, where all the other approaches are clearly worse here, and we get a perfect, or as good as it gets, I would say, with an eddy viscosity model. Perfect match to the spectrum, up to the cutoff frequency of the code, making full use of all the degrees of freedom that we have, and having an intelligent agent pick us this eddy viscosity here as we run it. And this is at least if you've worked a lot with turbulence and these simple test cases here, it's kind of hard to get such a good result. It's very hard to get such a good result if you want to tune this by hand. So we're very happy with these initial results. Here's just to show what happens to the actual eddy viscosity. So we initialized it as some Gaussian here, and then the trained eddy viscosity is actually something, or we can see that the trained eddy viscosity is actually something that is actually learned from this, or it's different from, it's not just a random noise that we put in there. This would refer to a eddy viscosity of a constant Smagorinsky model at CS 1.7 from the previous slide. And we see that what our model gives us, it's not a constant eddy viscosity, it not just picks one number, but it actually gives us a nice distribution that at least from these initial results also makes sense. Okay. Vishal, can you let me know if I have 5 more minutes, or if I should, this would be a good place to stop, but I could also go on for 5 more minutes. Could you indicate what's best to do here?
I think we're a little bit over time, so maybe it might be a good place to stop.
Okay.
Sorry.
Okay, sure. Okay, perfect. So let me just show on one what we're also working on is how we can transfer this to channel flow, and this works even greater for channel flow. But I'll stop here and come to a summary of my talk. So I've shown you 2 or maybe 3 examples of how we can use machine learning to augment CFD codes. The first one was a very simple, clear-cut case: supervised learning models for shock capturing, precisely locating shocks or other flow features in the flow solution, and then using this to actually improve the numerical scheme to be more targeted in its application of shock capturing. So this was a nice come full circle example. A little bit more messy is turbulence closures, and not so much from a machine learning perspective, but because turbulence closures in the LES context are ill-defined most of the time, meaning that unless you have a very simple, very well-defined, explicitly filtered LES scheme, which at least in my community, aerodynamics, people don't have, the closure term is a function of the discretization. That means supervised learning is probably not the best way to go, because it means that you don't know what you should be training on. You don't know what your Reynolds stresses, the thing you're trying to close, actually look like. They will evolve during the computation. So what could we do instead? One idea I've proposed here is use reinforcement learning. That's much more akin to a control problem, what actually is a control problem, where we can learn to take an optimal action by experiencing a dynamical system, observing it, manipulating it, and seeing what the outcome does. We've developed this. We've coupled our CFD solver to it. We've run it on the supercomputer. And we are currently looking at how to actually come up with modeling strategies that give us discretization-aware closure models. So for a specific discretization, aka for a different filter type, I can target now what my turbulence closure model should be. This is not just applicable to turbulence modeling, but essentially what this framework is now is, as I said, if you want an optimizable PDE solver. So things like flow control, for example, is also, of course, something that you can cast in this framework. And we're excited to explore what else we can do with this. Okay, so sorry for going over time. I want to thank you for your attention. I want to thank all my coworkers And here are some of the papers that we have been able to publish or have submitted on these topics. So hopefully there are some interesting questions or any type of questions from your side. So thank you for your attention.
Fantastic. Thank you so much, Andrea, for your fantastic talk. We do have a bit of time for questions. If anyone in the audience has a question, feel free to just unmute yourself and ask, or you can add it to the chat. That's fine too. So I think while people are gathering their thoughts, I was really interested to see the reinforcement learning. And in particular, like when you were describing it, I was expecting it to be like unstable, like a bit more unstable and potentially like might come up with the wrong answer. But you said like you tested it and it actually was like quite stable and obviously came to that stable result. Was that surprising to you that it kind of worked so well?
No, it's not surprising. Well, no, yes, it is. Sorry, let me rephrase it. Yes, it was surprising for us, and we honestly also ran into a number of issues with the reinforcement learning, which led to unstable results. So, getting it to from my perspective, the problem is that if you start off with a policy that's completely wrong, you will sample many wrong and unstable results. And the algorithm will never come up to the point where it can find a good direction, right? So if you start up in no man's land, so to speak, and you have no clue what a good strategy would be, then I think it's very difficult for reinforcement learning to find this initial path. From my understanding of literature, this is also a general problem of reinforcement learning. If you can nudge your reinforcement learning towards, this would be a good first, good safe, like with training wheels, right? Would be a good region to explore first, and gather some experience. Then it works rather well. Then once it's on this track, then for us it works well. With the caveat being, and this is an open question for me, is how do I define my reward function? All of this reinforcement learning is driven by what the reward function looks like. So how much reward do I get if my spectrum looks great? And how much reward do I deduce if it crashes? Okay, so how does this, and there is of course a continuum between those two, right? And how do I shape this? That's a question to the machine learning and mathematics guys. How do I shape my reward function in that space between those two? Is for us at the moment, honestly, a little bit of a trial and error. But looking at literature, I would expect that's the current state of the art.
Fantastic. That was a good response.
Andrea, I had one. At what is the highest spatial resolution of the grid that you faced a breakdown in the shock capture results? Like, did it capture well at even a big size of the grid as well?
You mean a very fine grid?
Oh no, a very coarse grid.
Very coarse grid. Well, let me go back here. Here, this is a test case called a forward-facing step test case. So it's just the step here, right? And this shock flow comes from the left and hits it. And usually people run this. Classical setup is 200 grid elements on in the x direction. And I have here 1, 2, 3, 4, 5, 6, 7, and maybe 20. Don't know. So this is a very coarse grid already, and I've seldom seen it run this coarsely. So I cannot answer your question. And we did this on purpose just to show, hey, I really have one element here, and I nicely have a 2D shock here, right? See, it's curved, nicely captured within one element. That's the reason why I ran it as coarsely. I would not do that if I were truly interested in the shock front here, but if you're interested in practical runs, right, you'll always have cases where you have airfoils. You need to coarsen the freeze stream up here to save computational time. So you will always have these regions where the shock should be stably and accurately captured and not give you any trouble. So that's why I have this coarse grid here. So maybe, but we haven't done a study of how coarse we can become.
Oh, okay. Okay.
But for me, this is really coarse.
Oh yes, of course. I mean, it's 1/10 of that, so it's quite good.
Really coarse. We've got a quick question in the chat, so I'll just read that out for the recording. First of all, saying, great talk, thanks. Can you comment on the applicability of other supervised learning methods, such as super resolution to LES?
Well, many people, let me again answer that a little bit with a history. When we started out doing supervised learning in the way that I've described, just learn from a DNS and then fit the Reynolds stresses, we were the first one or the second one to actually do that. And after us, many people have tried to do this for different equations and so on. And many of them have been able, or most of them have been able to repeat these successes, to confirm these successes, that it works very well. And then quickly people realized, well, these a priori great machine learning predictions don't serve me or are not useful. If I plug them into my code, it will blow up. So what people have been doing in supervised learning is a lot of incorporating physical constraints into their supervised learning. So for example, not just train to predict the Reynolds stress, but train to predict the Reynolds stress and a field that gives you positive dissipation. So, or incorporate symmetries into the prediction. So not just learn the target itself, but try to add some physical constraints to that. I mean, the other limit of that is actually pins, right? Where you essentially just enforce the equations directly. So this is where, and there are many ways in machine learning to do that, incorporate physical constraints. Or another, we also did that, didn't have the time to talk about it. Or another idea is to make the machine learning algorithm more robust by using something called, for example, stability training, that are tricks from machine learning. So problem is stability, and people have tried to do this physics-based or machine learning-based, or the one we came up with is take your prediction and project it onto something that is stable, like an eddy viscosity model. In terms of, and there are many variations of that theme. And in terms of super resolution LES, I've never worked with that, so my knowledge is probably to be taken with a spoonful of salt. I have. Well, in LES, what I can see super resolution doing is invert a smooth filter shape, right? So whenever you have a filter shape that is smooth, so that leaves you something in the higher modes there, it's tiny, but it's there. Inverting that with super resolution LES is something I can see. Where I have trouble seeing that, what should happen is I have a true cutoff. If I have a loss of information, LES, if you think about LES by definition must be a massive loss of information, otherwise we couldn't save computational time. So how to revert this loss of information, that's what super resolution learning is usually doing, reconstruct some modes that are not there. I'm skeptical. I have seen one paper where actually published in JFM where I thought the results indicate it's not working. JFM thought it is working. So maybe take even more salt that I might be wrong there. My answer is I would like to see I'd like to see some results on that before I can give you my final thoughts. So sum up again, long answer, supervised learning, a lot to do. Think about how you add constraints, physical constraints, symmetries, invariances, and so on. My current opinion is if I go to this trouble, I'll use something like reinforcement learning, which is, in my opinion, much more suited for a dynamical system such as LES, where supervised learning is not just, in my opinion, fitting to what an LES closure actually tries to do, be flexible, adapt to the discretization, adapt to the grid, and so on. But I might be wrong about that. So please don't be discouraged. I'm not sure, I don't know who's asking the question, but if you are a PhD student working on this, please don't be discouraged.
Great, thank you. Oh, they've said nice answer, thank you in the chat as well. So thanks for that answer. So any final questions from the audience before we finish up? All right, otherwise we'll thank our speaker one more time. So thank you, Professor Beck, and we'll finish up the talk for this week. Thanks.
Thanks a lot.
Thank you, guys. Yeah, thanks for having me.